Good morning to all. This is in continuation with the previous session. We started Unit 3 in the last session. Now, this is the continuation of that Unit 3. Let us start. Let us start. Now, we started Unit 3. Under Unit 3, this Unit 3 is for which one? Starts with Fourier integral. From Fourier integral, we discuss Fourier transforms as well as we discuss Laplace transforms. Now, in the previous class, we discussed Fourier integral. Now, we are discussing Fourier transforms and Laplace transforms. Now, students, try to not to be confusing with the word Fourier integral. This is the word integral. Next, Fourier transformation. This is Fourier integral. This is Fourier transformation. This is different. This is different. These two are different. Just you are supposed to make a differentiation between these two concepts. In Fourier integral, we use two integrals. In transformations, we use only one integral. Please make it remember. Whenever or as long as we are using the word integral, we are supposed to use two integrals. But in case of transforms, whether it is Fourier transform or Laplace transform, we use only one integral. That is the first and major difference between these two. Second point is that Fourier transformations and Laplace transformations, these two transformations are used for continuous time signal. This is used for continuous time signals only. Make it a point. This is for continuous time signals. Look at the word continuous. So whenever there is the continuous time signal, we are supposed to use either Laplace transform or Fourier transform. Only these two. You are also having another one. What is this one? Discrete time signal. For discrete time signals, we are using which one? Z transform. This is for discrete. We use Z transforms. Students have to understand these two. Now just we are in the third unit. In the previous session, just we concluded Fourier integral. Now just we are going to discuss Fourier transformations and the Laplace transformations as well, one by one continuation. So before entering into this concept, again I am reminding you, Fourier transformation, Laplace transformations for continuous time signals and discrete time signals for Z transformations. Okay. As long as we use integral, we use two integrals. Whenever we use the word transform, only one integral representing. Let us start. Now just look at what is Fourier transform. We can write F or F of t, Fourier transform of a given signal. F of t is equal to, how do you write? This is transform. Use only one integral between minus infinity to infinity, f of t into e power minus jst. This is transform. Transform means what? Changing a signal from one domain into another domain. In the present one, the domain is small t. Now after changing, the domain will become in terms of what? F of s. So now two variables, j is a complex number. Now with respect to t, we have to make it the integration. With respect to t means what? The outcome will be in terms of which one? F of s. That is Fourier integral. Now, one more point. In intermediate first year, you know that if f of a equal to b means what? A equal to f inverse of b. Same concept. Now, this is the Fourier transformation of f of t. That is f of s. If you get f of t, it is called inverse Fourier transformation. This is called inverse Fourier transformation. Now, here f of t equal to inverse Fourier transformation of what? F of s. In case of inverse, you have to use a constant 1 by 2 pi integral minus infinity to infinity. For what function you are finding? For f of s you are finding. And e power j s t in terms of ds. Look at students, in this integral there is no constant, but in the inverse the constant is 1 by 2 pi. Here limits minus infinity to infinity. Here in limits minus infinity to infinity. Same. Here f of t, here f of s. Exponential, exponential. There negative sign, no negative sign, positive sign. With respect to t, here you have to respect to s, because to get the function f of t. This is the Fourier transformation. Okay, now Fourier sine transformation. Fourier sine transformation. Look at the word sine. That means we write that Fourier suffix s for sine. Fourier sine transformation of any signal f of t. It is written as 0 to infinity. Which function for which we are finding the signal? F of t into sine. So it contains s of t with respect to dt. Therefore, the output is f of s. Look at Fourier sine transformation, the word sine. So here, if there is no s, it will become Fourier transformation. So you have to make it what? Yes, Fourier sine transformation. Here, in the Fourier transformation, the limits are minus infinity to infinity, but here the limits are 0 to infinity. This is sine, therefore only sine term will come. That's why the name is sine. So sine st. With respect to t, you make the integration. The output will be in the terms of s, f of s. Now, what is inverse? Inverse Fourier sine transformation. That is equal to, inverse means what? F of t. F of t equal to, take this f of s that side. This is f of s inverse of small f of s. That is equal to, now here there is no constant. Here in the inverse you make the constant 2 by pi. Integration is from 0 to infinity. Here in case of f of t, we have to make f of s. Because of sine, use the same term sine st. But in the previous case, we integrated with respect to t. But now we have to integrate with respect to s. That is Fourier sine transformation and Fourier inverse sine transformation. This is Fourier transformation. Now look at next one, Fourier cosine transformation. Fourier cosine transformation. So Fourier cosine means suffix c. Fourier cosine transformation of a function f of t is equal to integral 0 to infinity f of t. The name itself is cosine. So it contains only one term, that is called cosine, cos st into dt. The transformation will be from t domain to s domain. The transformation will be from t domain to s domain. Now, here, now we have to find inverse. Inverse Fourier cosine transformation. This is inverse. That is equal to, inverse equal to f of t into Fourier cosine inverse transformation of f of s. That is equal to, keep a constant 1 by 2 pi. There is no change in the integral f of t, but instead of ft we have to write f of s, the same cosine cos st ds. Now just look at, these are the three important concepts in Fourier transformations. So students have to remember that before entering into the second part of Fourier transformations, we have to study Fourier transformation, Fourier sine transformation, Fourier cosine transformation mainly. For each transformation, there exists an inverse. So inverse Fourier transformation, inverse Fourier sine transformation, inverse Fourier cosine transformation. Now, the remaining two belonging to one category, the above one belongs to another category. Another category means in the sense, here the limits are minus infinity to infinity, but regarding these two, the limits are 0 to infinity. 0 to infinity. Here in the previous one, exponential term will occur, but in these cases, because their name is concerned, sine means only sine term will appear. Cosine means only cosine term will appear. In the plane sine integral transformation with respect to dt, but in the inverse with respect to s. In the plane cosine transformation, the first integral could be with respect to t, but in the inverse notation, the integration with respect to s. So these three are very important concepts. Now regarding these Fourier transformations, all problems are moving around these three concepts only. So students have to remember very easily. That's why just have written all the three transformations on a single slot, on the single page only. Now here some others may write Fourier transformation f or f of t. In whatever way they write, both are same. So now Fourier transformation of a function f of t or signal f of t. This is the way of writing. For example, next one, Fourier sine transformation. Fourier sine transformation of a function means we have to write here suffix as s. Fourier cosine transformation means of a function means we are supposed to write here cosine. So these three make the entire domain of Fourier transformations. So again I am telling you that as long as we use the word Fourier transformation, students have to make it these 3 points very important. First one. The second part is Fourier transformations. In these Fourier transformations, general Fourier transformations. After Fourier transformations, Fourier sine transformation, and here Fourier cosine transformation. Now just look at Fourier sine transformation and Fourier cosine transformation. Now look at the binary tree structure of this transformation. The second part of this unit, because first part belongs to Fourier integral, second part belongs to Fourier transformations, third part belongs to Laplace transformations. Now today just we started the second part, that is called Fourier transformations. So as long as we discuss the word Fourier transformations, students have to understand that it contains not only Fourier transformations but also contains Fourier sine transformations and Fourier cosine transformations as well. For every transformation there exists an inverse of the transformation. So Fourier transformation, this is Fourier inverse transformation, Fourier sine transformation, Fourier inverse sine transformation, Fourier cosine transformation, Fourier inverse cosine transformation. So mainly 3 formulas, but indirectly another 3. So total 6 formulas we are having under this concept. So the remaining everything will be moving around these 3 only. So now we are going to discuss the signal problems that are moving around these 3 topics. Understanding? So remember that very easy concept. That's why to make differentiation among integral formulas, I make all this one. Just look at f of t, f of t, f of t, common term. Whenever there is exponential, this is Fourier transformation. Whenever there is sine, Fourier sine. Whenever there is cosine, this is Fourier cosine. That is the easy way of remembering these 3 transforms. So in the next session, we are going to begin with the problems on this one. Thank you.